Hi everyone, welcome to part 2 of figuring out an unknown compound. So right now we are looking at the carbon-13 NMR on our left. So what I did was I just wrote down all the chemical shifts and what the carbon NMR tells us. At first glance, it tells us that there are 8 unique carbons since there are 8 different peaks. So as you remember from the last video, the molecular formula is C10H12O. And so since there are 8 unique carbons and 10 total in our compound, that means there's going to be symmetry. So what we know is that we thought there was going to be an alkene, and that would have a chemical shift of 100 to 150 ppm. So there are 5 chemical shifts between there on our carbon NMR. And then we know that benzene carbon is a chemical shift from 110 to 175. Which we have 6 of those. And since we know that an alkene is from 100 to 150, there is only one that is above that range, but also fits into the benzene range, which is this highest chemical shift carbon. So we know that this is definitely going to be a part of the benzene ring, and the other ones could possibly be from either the alkene or benzene ring. And we know that since the chemical shifts of A and B are pretty low, we'd say those are going to be a methyl, most likely. So now what we can do is we can go down to our hydrogen NMR, which tells us a lot of information. So what I did was I wrote down the chemical shifts, as well as the multiplicity and the integration. So the integration, which is right down here, adds up to 12. So this confirms our molecular formula. So I over here are some expanded regions. So all the peaks are expanded except for the singlet right here, because it's pretty clear it's a singlet. So A, which we're going to say is up here, the lowest chemical shift, a doublet of doublets, pretty clear. C and D right here, those are both going to be doublet of quartets, with an integration of 1 for each of them. And then the next expanded region are E and F, and those look extremely similar. So those are doublet of doublets, and they each count for 2 hydrogens. So since each of these count for 2 hydrogens right here, and they look very similar, I'm thinking that they could be the hydrogens off the benzene ring because they have a high chemical shift. These 4 peaks over here are what could be a part of the benzene ring and or alkene. But since these are the highest chemical shifts, I'm thinking that these 2 are going to be our hydrogens off the benzene ring, which would also imply that there is the symmetric since there's 2 integration. So the next thing I did was I wrote out everything I know. And so from here, what I'm going to do is I'm just going to draw what I'm thinking. So from the last video, we know that we have a benzene ring fragment, as well as, like, we have confirmed that from the carbon chemical shifts as well, the hydrogen chemical shifts. So from the hydrogens E and F, I'm thinking since they're symmetrical 2 and 2, so I'm thinking that the benzene ring is going to be para substituted. And we also know that we have an ether from the IR, so this is that fragment. And then we also know we have some type of alkene somewhere. So what I'm thinking is I'm thinking that I'm going to try to put certain things together. So we can see that this this A hydrogen has integration of 3, so I'm going to think that's a methyl group, and it has a doublet of doublets, so it has complex splitting. So I'm going to think that would be near a double bond, and because it's also low. So I'm going to say that this could be that A over here. And then for B, singlet, also a methyl, but it doesn't have the same shift as if it would come off of a benzene ring. So I'm thinking that maybe it could be this over here, these hydrogens next to this ether group. And then since there's also, excuse me, since there's also symmetry in the carbon, I'm thinking that the symmetry is going to be here for these carbons. So what I'm thinking is, I think the ether could be on one side, and then the other substituted side could just be the alkene. So this would potentially fit as E and F would be over here. These carbon hydrogens would be over here, and then C and D. C and D would be here or switched, and then A would be over here, and B would be all the way over here. The next thing that we'd have to decide, though, if we said that that was going to be our compound, which it does match, is we just have to decide if our alkene is going to be cis or trans. So what would tell us if the alkene is going to be cis or trans is the J value. So a cis J value would be within about 10 hertz, and then a trans would have about 16 hertz. So the J value for, it's these two right here, for C and D, the J value for CD is 15.8, which is around that 16 hertz range. So we are going to say it's trans. So we can say that our compound is going to be trans because of the 15.8 hertz for JCD. Thanks for watching the video. I hope you enjoyed, and I hope this helped you out if you're trying to also figure out an unknown. So thanks for watching.